Thanks, Lynn, for the introduction, and thanks everyone for the invitation to give the talk. Observing global ocean health and carbon cycling, and really what are the status and prospects for BGC Argo in the U.S. Going to be a bit of a U.S. focus here. In part, as this map shows, to make the point, these are the current locations as of a day or so ago of all of the multi-sensor BGC Argo floats. Those are floats with oxygen, nitrate, biooptics, pH, so on. About 540 of those in the world ocean, but the point I'm going to focus in the US because 75% of these multi-sensor floats are American, US floats. And, the prospects, if BGC Argo goes away, it's going to go from a global array, all the yellow dots, back to a bunch of sort of local North Atlantic and Mediterranean and maybe a few Australian floats, kind of thing, but not global. So it's the U.S. contribution, I would say, that makes us global. I want to acknowledge all the people that have funded this. I'll keep repeating NSF, all of these floats, the vast majority of the U.S. floats funded by the National Science Foundation and the Office of Polar Programs, also for the SOCOM project, some contributions from the NOP program. NOAA has contributed significant number of float bodies to the program, and NASA has contributed biooptics to some of the floats as well. But the vast amount of the heavy lift has been NSF. And so I'm going to make it sound like I did all this work, but I didn't. There's a huge team that really did this at first in the SOCOM project, which was led by Jorge Sarmiento. Got us from a bunch of little experiments to basin scale, the Southern Ocean, and then the GoBGC project, which is taking the SOCOM concept to the globe. And so, folks deploying floats at Scripps, at the University of Washington, at Woods Hole. We build sensors, run a data system here. We have some leadership that started with Jorge Sarmiento at Princeton. Big symbol for NSF's contribution. This is all part of the International Biogeochemical project. And, we depend on NOAA for the data system, and NOAA has also contributed floats and has a smaller project for BGC Argo as well. So just to step back, Lynn mentioned this implementation plan we wrote in 2016 that was based on a number of observing system simulation experiments, other looking at scale lengths for biogeochemical variables and so on, and has been, the estimates in this 2016 paper have been sustained by other more recent assessments of float arrays. And what it comes down to is that you want about 1,000 floats with multiple sensors on them, spread out globally. If you really want to do things like constrained carbon budgets and so on. And gentle person's agreement, the U.S. is going to do half of those. As in Core Argo, the U.S. does half the floats. So U.S. would support 500 floats. So again, stepping back a little bit, what does the BGC Argo float see? So here's a typical float. That's an Apex float. We deploy different models, but here's a 4 years of data from a float deployed in the GoBGC program. It is started around 30 north, and it's just kind of done a nice little transect, multi-year seasonal cycles up the North Pacific. And, you measure temperature, salinity, I'm not showing here, chlorophyll A, oxygen, nitrate, pH. And then we compute other variables. We'll talk about this a bit more, but we compute things like dissolved inorganic carbon, not directly measured, but we use the pH and estimates of alkalinity to get the IC. And what you see as the float goes up, you don't see a huge drawdown, for example, in carbon down at lower latitudes. And as the farther north you go, you see more carbon drawn down each year. The mixed layer depth, which is the black line, starts to mix down deep enough to entrain nitrate, bring a little bit of nitrate to the surface, makes a chlorophyll spring bloom in each of these years as the float goes up. And yeah, it's a great view of the ocean, what you see from an individual float. But the deal is, we shouldn't really care about individual floats. We should be looking at the global scale. And so here, just as one example, we'll talk a bit about more about this, but lower figure, oxygen at 300 meters globally from the GLODAP program. Took them 50 years to collect all the data to measure this. This is the same oxygen at 300 meters, but from floats in the year 2024. And, I kind of challenge you, find a difference. I mean, they're pretty dang similar. We'll look a bit more at the differences, but even more important, over here, this is the oxygen at 300 meters last March, and we do it in April too if I downloaded the data, but I happen to have the data into March. We can do this month by month, and actually even with finer resolution down to about the 10-day typical cycle time of floats every 10 days. We can get in real time the distributions of chemicals and biogeochemical properties in the ocean. And so people are taking advantage of this in a really significant way. Started with this paper by John Sharp et al., Go by O2, neural network fitted to the float oxygen and shipboard data. We should use them both. And use the neural network, and then you use the high resolution Argo data to then the temperature and salinity from the higher resolution core Argo to map with monthly resolution oxygen throughout the ocean. Number of people are doing this. Taka Ito has a different version. Same thing. Shipboard and Argo oxygen mapped using machine learning, happening in China, happening in the European Union, and then people are using the data. The global upper ocean dissolved oxygen budget for constraining the biological carbon pump. Right. So we now have data sets in real time that just took us decades to obtain, and we're doing it now in real time. And, so what do you do with the data? This is just one graphic out of the Sharp et al. Paper showing the decline in oxygen. And, we're really at the point now where we can do this with monthly resolution. These are, the oxygen decline at 0 to 100 decibar, 600 down here, the dark line, 600 to 2000 decibar. You can do it. You can calculate productivity. Just kind of transforming what you can do, with BGC data. And it's important because look, this is so out of the World Ocean Atlas 2023. In a changing ocean, the shipboard observations are just going away. And if we didn't have floats, we would just be blind to the effects of climate change and so on. So this plot is the number of profiles of oxygen in the thousands from ships, red, and it has just gone down and down. This is year 19. You end up over here in 2020. We can barely see the ship contribution going in, and that's because science has changed. In the 70s and 80s, the science was mapping the distribution of chemicals. Now, you're focusing on DNA and iron and carbon and other things. The blue is then the oxygen sensor on a shipboard rosette. That's going away as well. And green are the float data, saving our rear. If the data is any good, right? And this plot is a comparison, crossovers between ship and float data. Mean difference. So it's float minus World Ocean Atlas bottle data at crossovers plus minus 1 degree in 5 years and in the same month of the year. And the difference is 1.3 micromolar, which is, in my mind, a phenomenally good agreement. Hard to do a titration to 1 micromolar. That's still a very significant offset. I will just say we are working our tails to understand why there are offsets, to correct algorithms and so on, so to really reduce the bias in all of our variables. But still, this is great. We can merge the data. I won't talk about the quality of the data, but it is sort of equally good for things like pH and nitrate. The float sensor data is very high quality, and it is enabling, hundreds of papers, very high profile papers, all kinds of topics. This is the number of papers from BGC Argo per year. It's going up, close to 100 this last year, probably be over 100 this year. People are using the data, doing some phenomenal things, which I will, get to in a little bit more detail here. So Some examples of what people do. This is a paper from Katja Fennell's lab, Adam Storr, graduate student, carbon-centric dynamics of Earth's marine phytoplankton. Our study demonstrates that profiling robots enable more reliable monitoring of Earth's phytoplankton, which is urgently needed to understand the impact of climate change. The point they make, of course, is this is the satellite, satellites basically see chlorophyll, carbon, particulate carbon down to one optical depth. Doesn't go very deep. Most of the carbon and chlorophyll in the ocean is below where the satellites observe. Phenomenally, if we really want to study change in biomass and so on in the ocean, we're going to depend on Argo, BGC Argo robots. This is a paper that I wrote with Mariana Biff, and we published a few years ago in Nature Geoscience. We often think, we've got satellite models of primary productivity. We think we're measuring productivity. It's really a model from ocean color satellites. But the profiling floats actually allow us now to measure productivity, gross oxygen productivity in the ocean directly. This is a plot of oxygen anomaly. That's oxygen minus the oxygen solubility for all profiling floats in the northern hemisphere, 10 north to 60 north, upper 20 meters. Looks kind of like a scattergram. But in fact, every day, this is local time of day, and every afternoon, oxygen is a little bit higher because of productivity, and every morning it's a little bit lower because of respiration over the night, a little bit of signal processing, and you can resolve the oxygen anomaly globally in the ocean. So here it is for the northern hemisphere. A little bit higher in the afternoon, a little bit lower in the morning. You can turn that this oxygen diel cycle into productivity. You can get an annual cycle of gross oxygen productivity. This is northern hemisphere, a little higher in the spring, decays into fall. You can get the depth resolved productivity, which you can't do with satellites. And you can take this and integrate it over the global ocean, get a number for global ocean primary productivity, 53 plus and minus 9. If you look at the satellite, they never provide you a plus and minus error bar in the data. But in general, satellite estimates of global ocean productivity run from about 40 to 60 petagrams of carbon per year. Those are really estimates. We're measuring it directly. We are at the point where we can possibly now see change in ocean productivity. Transforming our ability to look at ocean acidification, paper by Matt Masloff et al. In taking the ship and float data and merging it in the Biogeochemical Southern Ocean State Estimate, BSOSI, to create a map of pH in the ocean, and then to look at the change in time in pH and create a diagram like this, which is the pH trend, the change in pH per decade. So dark blue is minus 0.02 pH per every 10 years, 0.002 per year, pH going down. The zonal mean of these data, then with the overturning circulation overlaying on it, and you start to see regional changes in pH that make sense in terms of our understanding of the overturning circulation and so on. So really starting to be able to do this, at a global scale and really understand how there's variability in pH. There will be in acidification variability in the biogeochemical response to acidification. But you can then take this pH data and compute using our understanding of carbon system thermodynamics and various neural networks that have been fitted to the GLODAP type data and compute dissolved inorganic carbon. This is a figure from a paper we wrote a couple of years ago, just showing the float estimate of dissolved inorganic carbon versus direct measurements when the float is launched, and you get a really nice correlation, very low offset. Float data is always noisier than the ship data, plus minus 8 micromole per kilogram, but no offset, and you make lots of observations. You let the square root of n be your friend, and you reduce confidence levels and can do phenomenal things with DIC. This is a paper Jade Sauvé, a student of Alison Gray's, looking at the carbon budget in different zones, the Antarctic Southern Zone, the seasonal ice zone of the Southern Ocean, full seasonal budgets of dissolved inorganic carbon, the mixing across the thermocline, the uptake of carbon by the plankton, changes in the seasonal ice zone, small arrow to a big arrow just north of the seasonal ice zone. We have the air-sea flux, and so on. You can constrain the carbon cycle in ways that we just have not been able to do with essentially, they're estimates of DIC, but they are really well constrained by the pH observations and the alkalinity neural network. So alkalinity doesn't vary a whole lot. So we can do really nice estimates of it. But now that we have 10 years of data, we can actually start, Matt in his paper that I showed was merging shipboard and float data. We now have, with 10 years of data in the Southern Ocean from the SOCOM program, we can start to see the decline in pH directly from the shipboard data. This is a zonal, all of the float data from 50 to 55 south. You can do this in every zone of the Southern Ocean. You can do it in the Atlantic, Pacific, Indian. I'm just showing one example, but the point is, here is the slope, minus 0.0025 per year. This is computed, not just straight regression on the data, but there is a protocol developed by Adrian Sutton et al., best practices for studying ocean acidification. The data have been deseasonalized, corrected for autocorrelation, and so on to get an error bar, plus or minus 0.008. If I go back and look at Matt's, that's 0.0028 is what we're seeing at the darker colors right here. We can do this everywhere in the ocean. You can also then compute the partial pressure of carbon dioxide, and you see the PCO2 of the surface of the ocean going up at a rate of 2.7 microatmospheres per year. The atmosphere is going up in the past decade at about 2.5 microatmospheres, so very close. Things look great. The interesting thing, and the thing I think that is really has me most excited, amongst many things about the data, is the fact we can see the acidification rate, we can see the impact on carbon. We can now take the DIC numbers, which I showed that we estimate quite accurately, and compute the increase in dissolved inorganic carbon essentially everywhere in the Southern Ocean. We have 10 years of data. So this is work being done by Guillaume Lineger. He's a postdoc at MBARI. Work's been a bit on hold. Guillaume's been out deploying floats on the I-9 Go Ship cruise, just getting back. But the work that Guillaume has done, this is a map, zonal mean of the rate of DIC increase in the Southern Ocean. Okay, so what does that look like? Well, here is the recent paper, Jens Muller, Nikki Gruber et al. Just published their increase in DIC based on Go Ship and using the this is the anthropogenic carbon increase, determined using the EMLR technique. And in the surface ocean where EMLR doesn't work, they use tracer time distributions. Very similar. This is the mean from 2004 to 14. This is the data now. The biggest difference is this upper ocean area over here towards the equator, towards the subtropics. You need to understand this is estimated by sort of the indirect tracer time method, and maybe is the least understood in the GLODAP-derived data, but we are measuring it more or less directly. Integrate that all over the whole Southern Ocean, and you get a increase in DIC from the floats that looks very similar to the anthropogenic carbon increase that Brendan Carter, using his tool Trace, would estimate, which again, Trace is based in Go Ship observations. So in the past, we've sort of had Go Ship with 10-year resolution, but we are now with floats, we can get to sort of monthly resolution on increases of dissolved inorganic carbon. Why is that important? Well, there's this fundamental difference in the global carbon budgets between what we think the ocean uptake of CO2 is from FCO2 products. Those are products based on measuring PCO2 from ships in the surface. which is very sparse data, mapping it with neural networks. What we get from models, basically the floats are going to provide us a much more direct measurement that as the data accumulates, we'll be able to do. We can do it now in the Southern Ocean because of the SOCOM program, but soon, 10 years, we'll be able to do it globally and really measure carbon uptake by the ocean. Just other point I want to make is this is the float direct estimate of DIC increase. That's not the anthropogenic signal. There's, number of things you have to do to correct for inputs, outputs, and so on to get to convert that to anthropogenic. But the point that they're close, I think, is really encouraging. We will have a way to measure carbon uptake by the ocean more or less directly, more or less in real time with monthly resolution. Which really fits into the Global Greenhouse Gas Watch need. The G3W will provide monthly net fluxes of carbon. Methane nitrous oxide too can't do that. But with 1 degree, by 1 degree latitude, monthly resolution, we can start with BGC Argo to really contribute significantly to that. And I think that's super important to understand the role of ocean in the global flux, the global cycle of carbon, and ultimately, the effect on anthropogenic warming. The other thing that's, big news these days, marine carbon dioxide removal, MCDR, is really on a lot of people's radar screens now. We might have to do something to the ocean to try and help it remove more carbon. This is a paper by Phil Boyd et al. Looking at monitoring ocean carbon dioxide removal. And as they point out, the tool that we have to do this at a global scale are BGC Argo floats. It really is our only tool to really look in real time, look at, the impact of the kind of MCDR global scale carbon dioxide removal experiments. So couple slides. This is just showing the mean, a bunch of floats in the Pacific Ocean, between 50 and 60 south, a bunch of floats in the Atlantic Ocean, same latitudes. Here's it's day of year, depth down to 1,000 meters. We can start to see, for example, significant differences between the Atlantic and the Pacific over here in the Atlantic, much longer annual cycle that has high carbon in the surface. We see differences in the penetration of carbon to depth. The yellow line, 1.2 micromoles of carbon per kilogram, penetrates much deeper in the Pacific than it does in the Atlantic. These are all probably relate to differerences in iron in the surface ocean. We start to change things, and the floats will start to tell us about what is happening in the ocean. This was sort of a large scale view, but Mike Barenfeld's group, paper by Fox et al., then takes the float data, merges it with satellite data at the surface, and creates maps of POC concentration in the ocean that extend from the surface down into the mesopelagic, very high resolution. That really is where we need to go with this merging, multiple systems to get really the synergy. So I'm going to wind up. So I hope that's just a very high level scan of what floats do. I will just finish it by what is the current situation. So in the US, so there are two major programs running: GoBGC, NSF funded, SOCOM, NSF funded. There have been in the past, NASA exports program, NSF NASA exports program, some NOAA programs. The NOAA labs at PMEL and AOML have deployed a few floats, but really the bulk of the work has been done by GoBGC and NSF. So these numbers are the number of floats now operating in the ocean deployed by GoBGC, 260 some, SOCOM 140 some. These are the number of floats that these programs deployed in 2024. Altogether, the US programs deployed 120 floats last year. If we're going to sustain an array of 500 floats, if the floats have a 4-year lifetime, they'll be dying at a rate of 125 a year. We need to replace them at a rate of about 120 per year to sustain the array. The plan for 2025 on the left in the slash, these are the number we've deployed so far. These are the number remaining to be deployed for the rest of the year. And then this is what we have on order to deploy in the year 2026 for each of these programs. And we actually are exceeding our 125 target by a bit, in part because GoBGC got behind in its first year, took a while to ramp the program up. So we have an excess of floats in that program that are carrying over. But in general, we are putting in the water order of 120 to 160 floats over the next 2 years, and then we're done. There is no more funding. So GoBGC is formally funded through November of 2025. We have a 1-year no-cost extension that doesn't buy new floats. It just gives us time to put the floats that we have bought into the water. Okay. So we've ordered floats for the last year of GoBGC. There are no further float purchases that are currently funded. SOCOM is going forward. I didn't put it on here. It is funded, but in principle, I don't know whether we've shot ourselves in the foot or not, but GoBGC is funded to do the globe, including the Southern Ocean. You see the GoBGC floats starting to go in. SOCOM has reduced the number of floats it would acquire because GoBGC is going to do the job. So SOCOM's doing somewhere like 6 to 11 floats per year over the next few years, mostly targeted either towards special areas or more towards maybe, some more experiments. GoBGC will fill the Southern Ocean over the next, 2 years. So I said we need to deploy about 125 floats a year. We actually have improved the life of the floats. It had been 4 years when we started. We've gotten it up to 5 years. We've worked hard. The floats are running longer, and we think we can get it down to 110 floats a year replacement rate. Okay. So we wrote a 3-year proposal to NSF to continue GoBGC. It's been submitted, it's been reviewed, but no decision. And we know, the current uncertainty. NSF program managers believe that they are going to get a 40% overall NSF budget cut next year. So, we haven't been declined, but we have not been approved. The future, is quite uncertain, at least from NSF. What kind of money are we talking about? Well, this proposal that we sent to NSF to deploy 110 floats a year starts at $14 million a year to acquire and deploy floats. You have to operate the floats as well over future lifetime. That actually adds on another, $1.5 million to $2 million a year. So overall, we need something like 15.5 million years for capital and operations to run this, which is not a crazy number. That's actually less than the cost of running a global class research vessel. Something like Ravel is probably running closer to 20 million a year right now. A lot of money, but it's not a crazy amount of money, I think, for what you get. And I'm just gonna then finish it by saying, I think that GoBGC, SOCOM, BGC Argo are at the crossroads of ocean observing. Often, and I think I heard this at the end of Susan's seminar, people say, well, what can we get rid of to keep floats going? We should not think of it that way. Floats make observing by ships and satellites better. There's a huge synergy in running all of the systems. And, don't leave models out, because the floats provide, they provide this year-round data that really helps constrain and improve models, whether they're state estimates or Earth system models. Given, the climate challenges we face, I think we need them all. And with that, ready to take questions.
Yeah, so I guess the first question is, any news in terms of future funding that we don't know of, and what's the expectation? Anything there?
I can tell you we had a call with NSF yesterday, and GoBGC has $2 million in contingency funds, which we were assuming we would be able to access to operate in our year 6 unfunded or no cost extension. There is a cost in that we were going to cover from our contingency funds, which we were required to have. We were told we cannot have the contingency funds. So that's not good news. We'll recover from that. But is there any other news? No, other than I think the program managers feel like they really are going to get the president's budget request will be for a 40% reduction in the NSF budget. They think that will happen. Whether that is what Congress approves and the president, signs off on is a whole nother question. So that then leaves us talking to private foundations, which we are doing. Also, I don't know. Yeah.
So I guess one issue that came up in a previous discussion here was the connection with the Navy. Do you know anything about that? Or the Navy would seem like the ideal partner to pick this up from NSF.
They have not done much biogeochemistry, so the other half of this is that I think the core Argo is, also at risk, with uncertainty, and they're funded primarily through NOAA. And I think, the Navy might, exert influence to sustain core Argo. They really need to know the temperature and salinity for sound models and so on in the world ocean. But I don't know, they have a lot of interest in bioluminescence and so on, mostly in near shore though, where they put swimmers and stuff in the water. And whether they, we operate essentially in water that's 2,000 meters and deeper. Whether they, let's put it this way, I haven't had a serious conversation with anybody in the Navy about this. I will say the people I also have had what I would call serious conversations with various industries that depend on the data. There are people that run fishery models that really depend on Argo, and they're concerned.
Yeah, I'm wondering if some people who have already worked with the Navy should take the lead here to, push on that relationship. Maybe we have somebody in the Clive group who's, I don't know, to think.
All right, next we have Gail.
Hey Ken, thanks for the great seminar. I think you made a very good case about the crucial role of BGC Argo in terms of the global ocean and the carbon problem. But I was going to ask you if you could say a little bit more maybe about the societal and national benefits of Argo, BGC Argo specifically to the US.
Yeah, so there's a nice paper in Nature Communications or something about the economic value. It just came out last week or so on the economic value of the biological carbon pump, putting it at billions of dollars, right? We measure that. I mean, as I show you can see from the carbon, from changes in oxygen productivity, from nitrate uptake, we really do a great job, I think, at the global scale of constraining the biological carbon pump. There is starting to be much more of a connection to the fisheries community. So I think one of the most important things that we need to do, so people like John Sharp have shown that you can make these monthly scale neural network models of oxygen, of nutrients, subsurface chlorophyll, all doable. We have not operationalized that. So if you want to, I think super important, and people like John Sharp are working on this, to turn these into real-time monthly products of oxygen, carbon, nutrients in the ocean that would get used by the fishing, the pelagic fishing community, right? It's all doable. It's kind of a step outside of our normal, comfort level of going from science to actually operational products. But, the point I've made, I kind of wait every year to get to get the updates for the neural networks, the Peter Landschutzer's updates or whatever. We need people that are waiting, monthly to get the updates on oxygen, to get the updates on nitrate, so they can know where to send their fishing vessels and so on. So we really need to work on that. And that's a super social economic connection, and just things like deoxygenation and so on. We really need to understand that better. We could do a lot better than we're doing now.
Great, thank you.
Next, we have Monique.
Yeah, thanks. That was a great overview. So you've mentioned the fisheries a couple of times. Do you have concrete examples? Like, are there actual fisheries that we know are using the data? Is the chlorophyll assimilated in models that they're using, or something that can be pointed at that really makes a difference for them?
There are Australia. I should. God, I'm totally blanking on the name. There are papers where in Australian CSIRO in the fishery are running models for fishery, pelagic tuna in particular, that use, I'm going to now say, oxygen data. And I kind wow, where are they getting their oxygen data? And they're getting it from a model, right? The oxygen distributions. And so we're at the point, where we could start to provide that, monthly, neural network derived fields of oxygen for fisheries. So we had the Argo steering team just had a meeting a couple of weeks ago in San Diego, and 2 nice talks on the linkage to fisheries. Professor Chung from University of British Columbia and Cisco Warner, what's Cisco's position now? Was the chief scientist at NOAA, but on the role of BGC Argo and fisheries. So lots of interest. We're, to some extent, it's kind of like we have a new product and now we need to build a market.
So you're still at the point where you're trying to figure out how to make it useful for them rather than them actually using it today. Okay.
Yeah, I think the deal is that, we have to have an element of, build it and they will come, which is to start to produce these real-time monthly fields of things like oxygen. And I think people take it up. Right now, I can give you a field of oxygen. It's 2 years old, which isn't really very helpful. Very good for science. I can write a great paper about it, but it's not operational. And that's where we have to, go real time.
And since I'm here, another question that we kind of asked Suzanne also, in terms of the international participation, do you see the international community starting to step up to help more because of the current context, or how does that look in that space?
So a couple of things. So, at the Argo steering team meeting, huge concern about U.S. dominates. We do 50% of the core Argo floats, and we're actually doing 75% of the multi-sensor floats now. Have a huge influence, and it is at risk. And our European other colleagues are all saying they could go make now. We've sort of built the model. They could go to their governments and say, U.S. is going away. We need to step up. Here's our chance to really have an influence. But they're not going to be able to do it till they know, are we going away or not? It's sort of we need a signal of what's really going to happen to a large extent. So number one, they think they could make. They're now in a position where they could sell their programs, because right now there are, in Japan, there is a program sort of wending its way forward. It's gotten there's sort of a national large science programs competition. One is for Japan to do 20% of all of Argo, BGC, Core Argo, Deep Argo. And that's gotten down to the point where there are 2 competing programs, and that whole program has been kind of put on hold because the Japanese economy is not doing so well. I'm not sure what tariffs they're going to do, will it remain on hold for a long time. But so around the world, there is some effort to step up. right now, no, yeah, they're contributing half for Core Argo, 25% for BGC.
All right, we have time for a little more discussion. Natasha?
Yes, hi, Ken, thank you. That was a great overview and new information that, at least for me. So I would like to ask you if you could speak a little bit more about the uncertainties, particularly with respect to the spatial scales. So what is the spatial scales that we can go down to right now with, and with what confidence, given all the, objective and maybe subjective reasons why there are? And also, are we going to extend BGC Argo for undersea ice? Is that ever?
Yeah. No, well,
Yeah.
so undersea ice is happening. We have, 30 the Southern Ocean floats are running under in the seasonal ice zone. We probably, I don't know, Lynn, what do we have? 30 floats in that region we've sustained for multiple since 2014. Lots of floats, tons of papers, many papers written on biogeochemistry under float, undersea ice. The carbon budget that I showed from Alison Gray, Jade Sauvé's project, half of that was just north of the sea ice, and the other half was in the sea ice with floats. So that's happening. Okay, good news. Okay, check. Spatial scales. So 1,000 floats in the global ocean. That's one every roughly 6 by 6 degrees, right? Not high resolution. What has enabled people like John Sharp, so he develops a neural network for the floats that have oxygen, and the neural network is driven by temperature, salinity, location, depth, and time of year, right? And so then he can take the Core Argo data, which is now much higher resolution, 6 times higher, it's actually probably more like 10 times higher resolution, and use the high resolution temperature and salinity from the Core Argo floats to drive his neural network at sort of the Core Argo resolution, which is sort of, and ultimately you get the Core Argo, they map the data either objectively or with neural networks to sort of 1 degree by 1 degree resolution and monthly kind of scales. So it's not crazy to think that we provide products at that kind of resolution, 1 degree by 1 degree monthly, with sort of a trail where you can compute errors and so on. After that, it gets hard. There are lots of papers now looking at floats and eddies, and so all of these things like eddies get aliased into the signal. You can use satellite altimetry to find all the float profiles that are in eddies, and you can start to look at the statistics. So Liddy Kepler, Lynn's postdoc, beautiful paper on carbon inside and outside of eddies from floats, and she's got, I don't know, Lynn, 600 profiles in eddies, and in anticyclonic eddies, 600 profiles in cyclonic eddies, and so on. And you start to statistically look at things like that, the thing I showed, diel cycles, floats are still going up and down at 10 days, but if I treat the array as just one big sensor array that's sampling the ocean at all different hours, I can start to get down to hourly resolution. So there are some funny things that you can do. All these signals are aliased in, and you just have to find a way to tease them out at higher resolution.